For next question, that is question number 32. A straight cylindrical conductor is suspended with its axis perpendicular to the magnetic field of a horseshoe magnet, and the conductor gets displaced towards left when a current is passed through it. What will happen to the displacement to the conductor if the current through it is increased? So it's given that a cylindrical conductor, let's say this is a cylindrical conductor, and it's suspended. So let's say it's suspended by a stand. Let this be a stand. Okay, and is suspended with its axis perpendicular to the magnetic field. So of a horseshoe magnet, and there is a horseshoe magnet. Let this be the horseshoe magnet, which has its north and south pole, and the conductor gets displaced towards left when a current is passed through it. So let's say this is the wire that is wrapped and then connected to a battery. Let's say this is the positive end of the battery. This is the negative end, and then its other end is this is how it's connected to the conductor. Okay, now the conductor gets displaced towards left. So it gets towards left when the current is passed through it. This is the direction of the current. So let's say it gets displayed towards left. So what will happen to the displacement of the conductor if the current is increased? So this is the conductor placed in a magnetic field, and we know that when a current carrying conductor is placed in a magnetic field, a force X on it, and when the current is increased, the displacement of the conductor is increased as well. So therefore, the first one, the displacement is increased. Now, if the horseshoe magnet is replaced by another stronger horseshoe magnet, that means the magnetic field increases, and that means that the displacement also is increased. Displacement of the conductor is increased. Now, direction of the current through is reversed. If the direction of the current is reversed by changing the polarity, that means now the direction of displacement of the current is direction of displacement of the conductor is also reversed. So this means that the direction of current through it is reversed, means direction of displacement is now changed. So direction of displacement is also reversed. That means if it was moving towards left initially, it will move towards right now. The direction of displacement is also reversed. Okay, next one. Name and state the rule for determining the direction of force on a current carrying conductor placed in a magnetic field, and the name of the rule is Fleming's left-hand rule. So this is Fleming's left-hand rule, and this rule states that if we stretch forefinger, middle finger, and thumb of left hand mutually perpendicular to each other, and if forefinger gives the direction of magnetic field such that the forefinger gives the direction of magnetic field and central finger or the middle finger gives the direction of current, then the direction in which the thumb points gives the direction of the force. thumb gives the direction of force on a conductor or the motion of the conductor. So that means if we have thumb, forefinger, and the middle finger mutually perpendicular to each other, and let's say this is the forefinger, which gives the direction of the magnetic field, which is denoted by B, and this is the middle or the central finger, which gives the direction of the current, and this is the thumb, then the thumb gives the direction of the force or the motion of the conductor, and all these are mutually perpendicular to each other. This is Fleming's left-hand rule to find the direction of force on a current-carrying conductor placed in a magnetic field. Okay, now, okay, for the next one, it's given that we have to draw the pattern of the magnetic field produced around a vertical current-carrying straight conductor passing through a horizontal cardboard, and we have to mark the direction of current and magnetic field lines, name the state rule, which is used to determine the direction of magnetic field associated with the current-carrying conductor. Okay, so this is part B, and let's say this is the cardboard, and through this cardboard we have passed a straight current carrying conductor like this, be a straight current carrying conductor that is passing through the cardboard. Now the straight current carrying conductor is connected to the battery. Okay, and let this be the direction of the current. This is the conductor XY, and this is connected to a battery. Let there be an ammeter connected here. Let this be a proper circuit. So, and here, let this be a variable resistance, which is rheostat. Let this be variable resistance to change the resistance and hence the current. And let this be connected to a battery. Okay, this is the negative and the positive. So this is the direction of the current. And the current is flowing in the downward direction. And we know that at any point around a current carrying straight conductor, the magnetic field is in the form of the concentric circles. So this is a pattern of magnetic field. Now we have to give the direction. The direction of the current is in the downward direction, and if we use the right hand thumb rule. So this is the right hand thumb rule to give the direction of the magnetic field. So the pattern of magnetic field is in the form of concentric circles at any point, and this is the right hand thumb rule to find the direction of the current, sorry, the magnetic field in a straight current carrying conductor. And it states that if we grasp a current carrying straight conductor in our right hand, such that thumb points in the direction of the current. Then the direction in which the fingers curl gives the direction of the magnetic field. Thumb points in the direction of current. Then the direction in which your fingers curl gives the direction of the magnetic field. This is magnetic field. So if we use a right hand thumb rule here, and our thumb is pointing downward, then the fingers are curling in this direction, so this is the direction of the magnetic field, that is the anti-clockwise. If it is considered this to be a plane of the paper, so this is how the magnetic field lines would be, in this direction. And we use right hand thumb rule for this.